In the previous class, we looked at a few properties and types of sets, basically polyhedra and affine sets, and I also defined the notion of the dimension of an affine set and therefore the dimension of any arbitrary set, correct? Or the dimension of, so for a given set, the dimension is basically the dimension of the affine hull of that particular set. Right. So the question is, how do you define the dimension of an affine set? Right. If you are able to do that, then everything else makes sense. Right. So again, here's a simple exercise. So suppose that you have an arbitrary affine set. Okay. Take any affine set you want, and take any, let's call it x naught, from this particular affine set. All right. And using this set and this point from this set, you construct the following set, which is the set of all x minus x naught, such that x is in A. Okay, you basically take this point x naught and you shift the whole set by minus x naught. Right. So, for example, just to think about it visually, let's take two dimensions. Suppose my affine set is some straight line that doesn't pass through the origin. All right, and you take any point on this straight line. Let's say I pick this particular point. All right, say this point is 1, 0, right? And I look at a minus x naught, which is I take all of these points and I shift it by minus 1, 0, which is the same as shifting it vertically below by an amount by 1 unit. Correct? What would this, in this particular example, what would this set be? Yeah? Correct. But what special property does it have? It passes through the origin, right? Or more importantly, it's a subspace. Right? The claim is that you take any affine set and any point from this affine set, if you shift it by an amount of minus x naught, then this new set will always be a subspace. Okay. Now the dimension of this particular subspace is well defined, right? And this is what we are going to consider the dimension of the affine set, right?
The subspace depends on all. It's not.
Which one? So it doesn't matter which x naught you pick.
Subspace will include your origin.
The subspace will include origin, because if you think about it, just as a sanity check, we know that x naught, we picked an x naught from A, right? So I can pick an x. If I take x equal to x naught, which lies in A, then x naught minus x naught is a part of this new set. So x naught minus x naught is the origin. So you're guaranteed to have the origin as part of this particular set. Right? So that's the nice feature about this. right? And here's another exercise. Suppose I pick 2 points, x0 and x1 from this set A. Suppose A is affine, and you take some 2 points, x0, x1, that come from this affine set, and now you can define the following sets: A minus x0 and A minus x1. You know that both of these are subspaces, correct? Question is, do these two both give you the same subspace, or the other two subspaces actually different? Yeah? And why? Yeah?
Both will have same basis vector.
How do you guarantee that both will have the same basis vector?
They are just versions only, but within the same.
Sorry?
They are just different versions.
I mean, these two are sets, right? That's one thing to keep in mind. So the question is, so this is some collection of vectors, this is another collection of vectors. Question is, are these two collections different, or are they the same?
Definition they will be
Based on what definition? Based on what definition? How?
because this thing is space you are moving this thing, the whole point will still be
That's not the definition, right?
like let us take some the summation of alpha x
Um,
and then I subtract some x.
okay.
But the linear combination of and we get a new space.
Okay.
Now when we take a linear combination of that, it will more or less be every vector minus x.
So remember that A is an arbitrary affine set. Okay. You can't say that it's generated by some set of vectors or anything of that sort. What do you mean by basis vectors of an affine set? Okay, how do you define the basis vectors of an affine set? Or what is it? What does it mean for it to be a basis vector of an affine set? So I told you intuitively that every subspace is a shift. Sorry, every affine set is a shift of a subspace. We didn't prove that. We didn't prove that. That's effectively what I'm asking you to prove, right? The only property that you know about the definition of the affine set is that it is closed under affine combinations. That's it. That's all that you know about affine sets so far. Only using this property and nothing else, you have to prove these two statements.
There will be because
Yeah.
there will also be factor x1 minus x0 belongs to
X1 minus x0 belongs to A. Why does x1 minus x0 belong to A? So again, so you know that x1 belongs to A and x0 belongs to A. The claim is that x1 minus x0 belongs to A. Why? Is it an affine combination of x1 and x0? What affine combination is this?
could write it in terms of the time. Like you can take theta 0 and theta 1.
Okay.
And then a minus x naught is xa minus x naught plus theta to xb minus xa.
I'm sorry, can you repeat?
XA and XP are the ones that I'm using to define the starting point.
XA minus XP. Sorry, what statement are you trying to prove?
So A is XA plus theta into XP minus XA.
I'm sorry, X
A
A
plus theta into
plus theta into
XP minus
XB minus XA.
now XA minus X naught is XA minus X naught plus
So again, what are XA and XB?
the ones that are used to define the affine set A.
Again, so a set is affine. So are you assuming that XA and XB belong to A? Okay, and you're considering the following straight line that pass through XA and XB. Is that it? Okay, so the assumption is that take any XA, XB in this affine set A, and now you look at XA plus theta times XB minus XA. Go on.
Then you can write X naught in terms of that. And you put
How?
because we know that it belongs to A.
No, right? So it doesn't mean that X naught can be written in this form for any XA and XB, right?
It can
Oh.
because it belongs to.
So what does this define? This defines a straight line, correct? For example, in 3D, an affine set could be a plane. Right? Okay, so to prove that this is a subspace, firstly, to prove that this set is a subspace, what would you need to show? That's not enough, right? Yeah, so it's basically closed. What you have to show is that it's closed under linear combinations, right? If you are able to show, let me call this A prime. So if you show that A prime is closed under linear combinations, then it is a subspace, correct? So then how do you go about it? So I define A prime to be A minus X naught. So let's consider any, again, let's say XA and XB in A prime, right? If I'm able to show that every linear combination of these is guaranteed to be a member of A prime, then I'm done. I don't need to show anything further, right? And let's say alpha and beta in R. Okay. So what do I know about XA and XB? I know that since XA and XB belong to A prime, I can write XA as some XA, let me call this XA prime and XB prime. I can write XA prime as some XA minus X naught, and similarly I can write XB prime as some XB minus X naught, where XA and XB belong to A, correct? So what is alpha times XA prime plus beta times XB prime? This is alpha XA minus alpha X naught plus beta XB minus beta X naught. correct? So this, okay, right, which is alpha xa plus beta xb minus alpha plus beta times x naught, correct? Okay, yeah.
Is the linear combination perpendicular in the plane perpendicular to x naught?
No, right? So xa prime and xp prime are two arbitrary points from this set A prime, where A prime is A minus x naught, right? What do I know about A prime? I know that every point in A prime can be written as some element of A minus x naught. And I know that A is an affine set. Okay. So as long as I take some combination, so in particular, if I write this, if I take A alpha xa plus beta xb minus alpha plus beta. Okay, so first, if I sum all of these coefficients, what do I get? So xa belongs to x naught, xa belongs to a, xb belongs to a, and x naught belongs to a. So every affine combination of these is guaranteed to belong to a, right? What is an affine combination? Basically, it's a linear combination where the coefficients all sum to 1, right? That's the property that I want to use here, correct? What do these coefficients sum to? 0, right? But then I want to show, if I want to show that this belongs to A prime, correct? What do I have to show? I have to show that this combination is some element of A minus x naught. So let me add and subtract x naught to this particular quantity here. So I have alpha xa plus beta xb minus alpha plus beta x naught plus x naught minus x naught. I haven't changed anything else here. Now let me look at just these terms. xa belongs to a, xb belongs to a, x naught belongs to a. Correct? So each of these vectors are elements of this affine set A. What do these coefficients sum to? 1. Correct? So what can you say about this particular combination? It's an affine combination of elements from the affine set. So this is some xc minus x naught, where xc is an element of A. So what can you say about xc minus x naught? Belongs to A prime, right? So no matter how you start, you have some xa prime, xb prime, which belong to A prime. Their linear combination also belongs to A prime, right? So therefore this is a subspace. Right? Is that clear? Correct? So now we've basically shown that A minus x naught is a subspace. Correct? Any questions? So this is a concrete justification for the fact that every affine set can be written as some translate of a subspace. right? Similarly, if you take any subspace and shift all of the elements by a single vector, any arbitrary vector, that will also give you an affine set. Right? If A prime is a subspace, and x1 is some point in Rn. I'm assuming that's a subspace of Rn, but you can generalize it to a subspace of any arbitrary vector space. Then A prime plus x1 is going to be affine. A subspace is anyway affine, that is true. But this x1 need not come from this subspace. How is every subspace an affine set? It's closed under all linear combinations. So in particular, it's closed under linear combinations where the coefficients sum to 1. So the subspace is the most general form. Every subspace is, yeah, so it's helpful to keep that in mind. Okay, so let's maybe to clarify things. So far, what kind of sets or classes of sets have we seen? We've seen subspaces. We've seen convex sets. We've seen affine sets. And we've seen cones. Right? So let's try to look at this class of all sets. Now in this, somewhere over here is the set of all let me say that this is, yeah, say the space of all convex sets. Okay, so this is the class of all subsets of my vector space. All right, let's take Rn. All right, all possible subsets. They can have any weird structure, doesn't matter. And within this special class is this class of convex sets, convex subsets of Rn. All right. Now, what can you say about the class of affine sets? Is every affine set convex? Why? Why? So I'm asking, the question is again, let me ask the question again. Is every affine set convex? Yes. Anybody who doesn't agree with it? How many of you agree with the fact that every affine set is convex? Okay, almost everybody has raised their hand. So every affine set is guaranteed to be convex. All right, so this is the class of all affine sets. So this part is fine, right? What about the set of all subspaces? Is every subspace convex? Every subspace is convex because convex combinations are special. It's a special category of linear combinations, and subspaces are closed under all possible linear combinations. Right? Is every subspace an affine set? Again, it is because affine combinations are also special subclasses of arbitrary linear combinations. So every subspace is an affine set. So this is the set of all subspaces. Okay. So you have this inclusion, right? So every subspace is an affine set, and every affine set is a convex set. That is what you're guaranteed. Now, what about cones? Where do they sit in between? Is every cone guaranteed to be convex? No, we just saw that, right? You take the union of two rays. That's an example of a cone which is not convex. But there do exist convex cones, right? That's for sure. What about affine? So let me. I should have drawn it a little better. I'm going to move this to one edge. Okay, so this is subspaces. There's a specific reason why I'm going through all of this difficulty. So we know that every. Okay, so we have cones which need not be convex. But what about affine sets? Is every affine set guaranteed to be a cone? No, right? You can take a straight line that does not pass through the origin. This is not a cone. What about a subspace? Is every subspace a cone? Every cone is not a subspace for sure, but is every subspace a cone? It is, right? You all agree with this. So the inclusion looks something like this, right? So you have cones which are not convex. You have cones which could be convex but are not affine. But if you have a cone that is affine, then it must be a subspace. Right? Because again, every affine set is some shift. If you think about every affine set as a shift of a subspace, a cone should always contain the origin. And if the affine set has to contain the origin, it should be a subspace. So the inclusion structure looks something like this. Right? So this is the class of all cones. Question? Which one? Every subspace is a cone, right? That's the point. So this pink region includes the entire green region, but it doesn't include anything outside. So there's no other affine set which is not a subspace but a cone. Because by definition, if the set is affine and a cone, it should contain the origin, which must mean that it should be a subspace. A subspace is an affine cone. That's true. Yeah. Every subspace is an affine cone. True. Well, a subspace is usually something that's more fundamental, that's defined before you define an affine set or a cone. So yeah.
But it works both ways.
Yes.
Subspace
Yes. Yeah. Right. You can find convex cones which are not subspaces or which are not affine. Right. You just take a ray. That's an example of a convex cone which is not affine. And similarly, you can find cones which are not convex. Any questions? It's helpful to understand this inclusion properties.
want to include All of it. No, sorry.
No, it's not,
All
right?
of subspaces are included.
All of subspaces are included. That's why I put this all of subspaces to an edge, right? Yeah, this whole region is subspaces. Right? Any other questions? Okay. All right. So we've seen that A minus x naught for any affine A and any x naught in A is guaranteed to be a subspace. So I'll leave this as an exercise using similar ideas. Essentially, it's the same sort of idea that you have to use to show that A minus x naught is going to be equal to A minus x1. Right? So in other words, this subspace is unique. All right, so a few more definitions which will be helpful at a slightly later point. So recall that in the last class we saw an example optimization problem. Correct? We started off with a combinatorial optimization problem, which was to find the maximum weight perfect matching in a graph, in a bipartite graph. And we formulated this, we sort of relaxed this to give a linear program. And we could somehow solve this linear program very efficiently. And by chance, it so happened that the solution to the linear program was actually equal to the solution of the original combinatorial optimization problem that we had. And I stated some facts that the constraint set of any linear program is guaranteed to be a polyhedron. Now that is fairly straightforward just by the definition of a polyhedron and looking at the constraints which each of which define a half space. But then I also said that if the constraint set is a polytope, then the solution of the linear program is guaranteed to be a vertex of the polytope. A vertex is something that you can visualize, but we need formal definitions of each of these little things, right? If I give you some arbitrary set of constraints, what does it mean for it to be a point, let's say, inside the set, or on the boundary of the set, or on some vertex of the set? We have some intuitive understanding of what these objects mean, but we also need a formal definition. So if I give you an arbitrary point, how do you check? How do you verify whether it's a point inside the set, whether it's a point in a boundary, and so on? Because in the end, when we try to design algorithms, typically we'll try to look at algorithms that are iterative, where you start with an arbitrary point within the constraint set, and you keep moving along until you reach a point of minimum or maximum. And you always want to know where you lie within your set of constraints. Are you somewhere at the edge? Are you somewhere inside? And each of these can lead to different sort of phenomena, as we'll see later. So we've already seen some of these notions, but perhaps not defined carefully enough. So for any given set, we want to say what does it mean for the set to be closed? What does it mean for it to be a boundary point? What does it mean to be a point inside the set? Okay. So so suppose I give you an arbitrary subset of Rn. It could be an arbitrary subset of any metric space for that matter. But again, we'll only focus on Rn. The closure of A is going to be the smallest closed set that contains A. Okay. And typically, whatever optimization problem that we'll try to design, we will assume that the set is closed, and we will be operating within the closure of the set of constraints. Okay. Because most optimization algorithms that we'll deal with work with closed, at least that's a minimum requirement of being closed. That's the only case where you can give certain guarantees on the set, or on the algorithm. So this is the smallest closed set that contains A. Well, again, it's a definition, but it doesn't give us anything useful, right? How do I visualize the smallest closed set that contains A? Or what more? So I'm given the set A, so obviously I have to potentially have to add some more points to make it a closed set. What are those points that I have to add? Right? Not necessarily just the boundaries, as we'll see in a little while. Okay, that's why it's important to define these things carefully, because okay, what is the most common example of an open and a closed set that you think of? Yeah, yeah, open interval a comma b and closed interval a comma b. So what would be the closure of open interval of a comma b? Closed interval a comma b, wherein you just add 2 points at the two ends, and that becomes a closed set, correct? But let me give another example. Suppose that A is the set of all rational numbers. All right, is this set closed? Firstly, why? Correct. So basically, I can find a sequence within a Cauchy sequence of rational numbers which doesn't converge to a point. So now, obviously, I need to fill in points. What do you think is the smallest closed set that contains the rationals?
Plus all the
How do you define an irrational number? Is E irrational? Have you heard of the term transcendental? Is transcendental irrational?
Sir, there might be sir,
Sure. Yeah.
All rational numbers plus all rational number multiple with E. I think will be the.
Can you write root 2 as a multiple of a rational number with E?
But is there any like sequence that any rational sequence that converges to
1.1, 1.4, 1.41, 1.414, 1.41, so on. You can have multiple such sequences, right?
real numbers?
Yeah.
Even transcendental. Can be represented by the incorrect action.
Correct.
Take that as the sequence. And then any finite cutoff will be of irrational. So that's why the closure has to be.
Yeah. So basically, the closure of the set of rationals is indeed the set of reals. But now the points that you have to add are not boundary points, so to speak, because you have to fill everything in between, right? So in a sense, the set of rational numbers has a lot of holes in between. It has holes everywhere, right? And you have to fill in all of these holes everywhere. Rational numbers are dense in the set of reals. Yes. I know you've done a course in real analysis, so you know this, right? But that you're perfectly right, right? It is the set of rational numbers in a sense is dense within the set of reals, but so the appropriate notion to see what kind of points have to be added to A in order to make it a closed set, right? So the question that I'm trying to ask is, I'm given the set A and I want to construct the smallest closed set that contains A. Correct? That's what I want to know. So what qualifies for a point to be added to A in order to make it the smallest closed set or the closure of A? If you had to guess, right, based on what you just said, what would it be? How would you? You know what a limit point is. That's what I'm trying to get to, but just in terms of what you've already seen for closed sets.
Every sequence for A and just add all the limit points for every possible sequence.
Correct. So basically, you take all convergent sequences from points in A and take the limit of each of those convergent sequences. That gives you and you add all of these points that is guaranteed to, if you add all of these points to A, then that will become a closed set, right? So that's one way of putting it. Another way, slightly simple, which doesn't involve sequences, is the following. So again, I'm trying to define this notion of a limit point. Right. So some x naught is said to be a limit point. So one way to define this is if it can be represented as the limit of some sequence of convergent or Cauchy sequence of points from A. Right. Another way to say this is, if I'm able to find, for every epsilon greater than 0, if I'm always able to find some point from A that is within an epsilon distance of to x naught, then that qualifies as a limit point, because then I can construct a sequence, a Cauchy sequence that converges to x naught. If for every epsilon greater than 0, I can find some x that is in A, but different from x naught. Okay, such that this x is within epsilon distance to x naught. All right. So there are a couple of nuances over here. So firstly, you should be able to find a point that is arbitrarily close to x naught within the set A, but the other point to note is that this x can't be equal to x naught. Okay. So let's try to break that down. Okay, so before that, basically the closure of A is simply A union the limit points of A. That's how I'm going to define it. There's another notion, again, there's a slight difference depending on which reference you take, but most of them agree that this is the definition of a limit point. There's also a definition of a closure point where you allow x to be equal to x naught. But in here, we're going to demand that x is not equal to x naught. It will. I'll give an example. Right.
It will be identical to A, right? If we show x.
I mean,
So relax the condition x.
not necessarily.
I take a point itself, then.
I mean, here I'm allowing. So remember that. Okay. One thing to keep in mind is that x naught need not be a point of A. Okay. So let's see some examples that will make it more clear. Okay. This down. All right, let's take the example A equal to open interval 0 to 1. All right. Now here, So take any point within 0 to 1. Let's take half. Is half a limit point of A? Yes. Yes, because you take any epsilon greater than 0, you can find some point in A not equal to half, but belongs to A. Okay. You're all convinced that half is the limit point? Okay. So in this case, half is a limit point of A, but half is also a point of A. Okay. Is 1 a limit point of A? Yes, it is a limit point of A because you take any epsilon greater than 0, you can find, so every 1 minus epsilon for every epsilon greater than 0 is actually a point of A. But 1 is not a point of A, right? So the limit point can be a point outside A, correct? Right? Yeah, so in this case, this is not a closed set because there exists a limit point which does not lie in A. If every limit point is a point of A, then it is closed. In fact, that's one of the ways, that's usually the way you define a closed set. All right. Similarly, is 0 a limit point of A? Yes. Can you find any other limit points of A which are either not A or 0 or 1? No. So basically you take any point which is strictly greater than 1 or strictly less than 0, that will not be a limit point of A. Okay. That's good. Now let's take the set of rational numbers. Okay. Is every rational number a limit point of Q? Why? Okay, again, let's use the definition over here. Basically, you take any rational number, consider any, let's say R or X, which is in Q, correct? Can you find a point that is another rational number that is arbitrarily close to this rational number? You can, because you can just take X, say plus 1 by n for large enough n. So for example, if you want within distance epsilon, you could just take X plus say epsilon, or the rational number that is closest to X plus epsilon. Yeah, maybe the easiest thing is X plus 1 by n, where you choose n large enough, right? Effectively, n should be, you take any n which is greater than or equal to 1 by epsilon. That will do. Right, so every rational number is a limit point. Every irrational number is also a limit point. In fact, every real number is a limit point of Q. All right. So again, in this case, every point of Q was a limit point of Q, but there also existed points in between that were limit points of Q. Okay, is this okay so far? Great. Now let's take, say, the set of integers. Right? Is every integer a limit point of Z? So the question is, let's take the point 0. So 0 is an integer. Is 0 a limit point of Z? No, right? So so none of the integers are limit points of Z. What about non-integral points? Yeah, they're also not. You take any rational number which is not an integer. Is that a limit point of Z? No, right? You take an irrational number that is not an integer. Is that a limit point of Z? So you take a point which belongs to this set itself. Take an integer. Take 0. Is 0 a limit point of Z? That's okay. But of course, in this case, 0.5 is not a limit point of Z. But for example, over here, right, root 2 was a limit point of Q, right? But root 2 is not in Q, right? Just because a point is not in the set doesn't mean that it cannot be a limit point. And just because it is a point in the set doesn't mean that it should be a limit point. That is something to be kept in mind. All right. So Z in fact has no limit points. You take any point in R, it is not a limit point of Z. But Z is a closed set because it has no limit points. So the closure of Z is Z itself. Right? So it's a subtle thing. Correct. Yeah, true, exactly. Whatever. But I'm just following this particular definition, right? Yeah. Question.
Yeah. How is this concept of limit point of view different from the notion of limits of the sequence?
It's essentially the same, but here instead of defining it in terms of sequences, I'm defining it in terms of sets, right? Because I mean the reason why this is sometimes more useful is because in terms of sequences, everything is in terms of whether or not you can construct a sequence, correct? But here everything is purely defined in terms of whether you can find a point that is arbitrarily close or not. Everything is defined in terms of x naught, but effectively you can show that both of them are equivalent. In some cases that notion is helpful, in some cases this notion is helpful, and that's really where the notion of the limit point comes from, basically, in terms of limits of sequences. That's why they have the same name, limit, right? But the only subtle point is that here we're basically taking x naught equal to x naught. So this essentially avoids trivial sequences like x naught, x naught, x naught, x naught, x naught, right? We want to come up with some non-trivial sequence that converges to this particular point x naught. Any other questions?
The closure of the set.
Correct.
We're going to take the original set, find all its take
Yeah. Take the universe.
Now we can ensure that in this new set which we just formed, we're calling it closure of we call it A dash.
Yep.
If I were to take the limit points of A dash,
Correct.
I wouldn't get any.
You wouldn't get any new ones. Yes. Yeah. Now again, if you go through it in detail, you have to prove that statement as well. Okay. But yeah, there's only so much we're going to be able to do here. But essentially, in a basic course on real analysis, you will see that the closure of A, or the closure of any closed set A, is the set itself. Right? But for now, we'll just use that as a fact. Okay? Yeah. The only point that I wanted to make over here, that I wanted to bring to your attention, is that a limit point could be a point within A, right? A limit point could be a point outside A, but not every point of A necessarily has to be a limit point of A. Okay, just keep that in mind. So essentially all of this, sort of these notions happens when the set A is not discrete. Sorry, the set A is discrete. Okay. All right. So that was about, and also note that this is an infinite set. Okay. Both Q and Z are countably infinite, but in this case, every point is a limit point of, every point of Q is also a limit point of Q. But in this case, no point of Z is a limit point of Z. Right? Because they're kind of spaced apart. They're not close together in some sense.
But in the sequence definition, every point of Z can become.
Yeah, but then that can only happen for almost trivial sequences, because if you take any convergent sequence of integers, then effectively, okay, in the beginning you can have any arbitrary points, but eventually the same point has to be repeated infinitely many times. Okay? So that's not an interesting sequence, so to speak. That's why we don't classify those as limit points of this set. Okay. Okay, good. So just as we defined the smallest closed set that contains A, we can also think of the largest open set that you can construct within the set A. Right? So the interior of A is the largest open set within A. All right. And this also happens to be basically the union of all open subsets of A. All right. Now, again, why am I worrying so much about closure, interior, all of these things? If you think about, let's say, an algorithm like gradient descent, which you may have some sort of intuition for, let's suppose that you're currently sitting in some point inside the set, within the so-called interior of the set. Now, an optimization algorithm like gradient descent will start from a point. At every step, at every time instant, you're basically going to pick a direction and you're going to take a step in that particular direction by a certain amount, right? As long as you're within the interior of the set, of your constrained set, it doesn't matter. You're free to go in whichever direction you want, correct? But now suppose you're actually sitting on the boundary, so to speak. Then you're not really free to go about in any direction, right? You can only take a step in the direction which lies inside the set. Correct? So you do have some constraints. You don't have all degrees of freedom that is available to you. You need to be able to distinguish whether you are within the interior of A or whether you are in the so-called boundary of A, which we'll define next. All right? And it becomes a little more subtle as to whether you have all degrees of freedom available or not, and we'll just see in a moment. So let's look at, so this is the union of all open subsets, or it's the largest open set within A, right? Again, quick examples. Say I take the set 0, 1. What is the interior of this set? it is the open interval from 0 to 1 of A is basically the open interval from 0 to 1. So basically, if you have some sort of an optimization algorithm where you move in a sequence of steps, right? At any point, is it a particular point, and then you take a fixed, you move in some arbitrary direction with a fixed step size. Then, as long as you're in the interior, and then it is possible to move in any arbitrary direction, of course, but how much you can move depends on how close you are to the boundary, right? But as long as you're within the interior, you're safe, so to speak. All right. Now let me take the set A to be the set of all integers. What is the interior? Sorry? Phi. It's the empty set. So firstly, the set of all integers is not open. And can you construct any open subset of A? You can't, right? By definition, a set is open if you can fit in an open ball of non-trivial radius inside it. Correct? Similarly, set of rational numbers. Is Q open? Take any rational number, okay, and draw an arbitrarily small ball around it. Is every point within the ball guaranteed to be rational? Yeah. Right? That's the definition of an open subset. Right? You should be able to fit in an entire open ball within around this particular point. Right? So this is also empty.
It is countable, is it?
In fact, if it is countable, it is the interior will be empty. Okay, but there's another subtle point that I want to bring in here is that just because it is uncountable doesn't necessarily imply that it is going to have a non-empty interior. So for example, let's take the following set, say the set of all x1, x2 in R2. Okay, let's say that which satisfy x1 plus x2 equal to 1. What is the interior of A? Yeah?
You can't find a unit, non-trivial ball.
You can't fit a non-trivial ball inside this because it's in a so-called smaller dimension, right? So this set has dimension 1, it has a fine dimension equal to 1, but you're actually living within R2, right? You can't find you can't fit in a two-dimensional ball within this set A, right? So geometrically, this is your set. You take any point, the ball will always protrude outside your set. It is uncountable, but that's what I said. Just because it is uncountable doesn't necessarily mean that it has non-empty interior. If it is countable, then it will not have it. Then the interior will be empty. But the reverse is not true. Yeah, there's another question. Which one? Yeah, that will also be fine. Yeah. Yeah, there are a number of ways to construct sets which have uncountable sets which have empty interior. but sets like the Cantor set are not particularly interesting for us, right? So for me, sets that are interesting are basically those that I can express using finitely many constraints, right? Even with just one constraint, I have an empty interior, right? Great. Just as we've defined the closure and interior of A, I also want to define the notion of a boundary of A. And the boundary of A can you guess what this should be?
There are points inside and outside.
Inside and outside.
Closure minus interior.
Yeah, so it's basically the closure minus the interior. It's the closure of A minus the interior of A.
Definition of interior like fully helpful because
You're right. This interior is not, this definition of interior is not very helpful. That's what you said, right?
if I want to reduce x1 square plus x2 square,
Okay.
the line would still lie in my interior.
I'm sorry. Can you?
Line
Yeah, I understand. What you want to, okay, let's take the following example. Let me add in some more constraints. This line over here,
What is the closure of
the closure of this line is the line itself. This line is closed, yes. I mean, this set A is closed, right? Again, remember, just because a set is closed doesn't mean that it is not open. Right? Let me add some more constraints. Say that x1 should also be between 0 and 1. Okay, just for the sake. So the set will in fact be this line segment. Right? Now again, when I'm talking about optimization algorithms, I want some notion of, well, this is my constraint set, which maybe lies in a smaller dimensional affine space, but I also want the notion of points within the boundary restricted to this space, and also the points which are, so to speak, inside my constraint set. Correct? I think that is what you were trying to get at.
My boundaries would be the end.
Agreed. So intuitively, when I say this particular set, this particular line segment, you would say, like intuitively, you would say that these 2 points are the boundary points of this set, and everything that is strictly between these 2 endpoints of the line segment should be kind of the interior, right? So that's why we are going to define what I call the relative interior of A. Okay. Again, the main problem that we're trying to address is that your constraint set, or it may be lying in within a smaller dimensional affine space, right? For example, it could be subsets of some line in R2, or maybe a subset of a plane in R3, correct? So for sets of this particular form, how do I define the notion of the boundary, of what it means to be a boundary point and what it means to be inside the set? Correct? So that's what I'll call the relative interior. So we'll say that X belongs to the relative interior of A if, okay, if basically you can fit in a sort of smaller dimensional ball inside X, sorry, that is around X but within A, greater than 0, such that I look at, let's take the n-dimensional ball centered at X of radius epsilon. Now if this lies within A, if it lies completely within A, then in fact it's an interior point, right? And that's not very helpful to us. So what I want to look at is a sort of smaller dimensional ball. So I'll just restrict it to the affine hull of A. So this intersection, affine hull of A, should lie within A. Okay. Let's maybe
Why
take.
are you doing it?
We'll just see that. Okay. Let's again go back to the example I had earlier. Okay. Wherein the set that I'm interested in, the set A, is maybe a line segment. This is my line segment. This is the line, and maybe the line segment is basically this. All right, this is my set A. Now let me take, okay, intuitively, what would you call an interior point of A? Let me pick some particular point. Let me take this particular. Would you classify this as being inside A, in the relative interior of A? What do you say? Yes, you would all intuitively say that this lies inside A, and this point, on the other hand, does not lie inside A. Correct? Let's use this definition to see whether that is true or not. Okay, let's take this particular point and let me draw a ball of radius epsilon around it. Epsilon is something that is very, very small. If I take this entire ball, it comes outside A, it protrudes outside A. But what is the intersection of the ball with the affine hull of A? What is the affine hull of A? It is this entire straight line. So what is the intersection of this ball with this? It's basically a line, it's another line segment, right? It is basically this particular line segment, right? Agree with me? And this line segment is contained within the set A. So by this definition, yes, the green point that I drew earlier is in fact in the relative interior of A. It doesn't lie within the interior of A because the interior is empty, but it lies within the relative interior of A. Okay, fine. Now let me take this other point over here. All right, something that intuitively this should not lie inside A. It lies at the edge of A. Now let me draw a ball, no matter how small I make the ball. I take the ball, the intersection of the ball with the affine hull is another line segment. But no matter how small I choose epsilon, it's always going to go outside A, right? Because this edge above is always going to be 1/2 of this particular set is going to be outside A. So this green point, so this point, so this is in the interior of A, whereas this point does not lie in the interior, the relative interior of A. This point lies in the relative interior of A. Okay. Correct. So it is another line segment, right? Because what is the, because part of that line segment goes outside A, right? Right? Only one half of that, of the blue line segment is within A, one half of that line segment is outside A. Correct? Question?
Even with respect to ball of some dimension, radius dimension.
Correct, but which ball? So that's exactly, that is what I'm doing effectively, but I'm always restricting myself to the affine hull of A. So basically, this is actually, I mean, this is a set, the lower dimensional set in a higher dimensional space, and I want to go down to that lower dimensional set. But so what is the appropriate lower dimensional set on which I can operate on? That's basically the affine hull of A. No limit point can be in the relative, why not? So you take any point inside this line segment, that is also a limit point of A, right? Does that answer your question? Okay. Right. So, and similarly, I can define the relative boundary as the relative boundary of A as simply the closure of A minus the relative interior of A.
Boundary of A minus relative.
I'm sorry.
Boundary of A minus relative.
A boundary of A minus the relative interior of A. Why not just define that to be closure of A minus relative interior of A? Let me think. So closure. Yeah, so effectively that would be that would be the same.
Relative boundary of A will lie on the affine hull of A.
The relative boundary of A will lie within the affine hull of A. Yes. Again, it's a subtle point, but the closure of A will lie within the affine hull of A.
Definition of the affine hull.
Which is
Closure of
no, right?
the affine hull of A is the closure of.
No. Closure is a different notion from affine hull.
Okay, so affine is just the linear combination.
Correct. Affine combinations. Any other questions?
Is there a relation between the relative interior of A and the interior of A?
The relative interior of A and the interior of A? Well, if the set is open, then the relative interior is equal to the interior. Or if the affine, so if the interior is non-empty, then the relative interior is going to be equal to the interior. So okay, when is the interior non-empty? Suppose that I give you a set and it so happens that the interior is not empty. What can you say about the affine dimension of A? It should be equal to n, or the dimension of the ambient space, right? Because you can fit in an n-dimensional ball within your set A, correct? So in that case, the affine hull is equal to Rn itself, correct? And in that case, the interior will be equal to the relative interior. Okay. But one thing to note is that let's take this. Let's again go back to this example. What would the boundary of this set be? Yeah. Can you speak up? Like, I didn't hear you. It is? I'm talking about the boundary, not the relative boundary. The whole set, right? So every point is a boundary point. So that is why in our context, the classical notion of boundary is not good enough. And that's why we use this other notion of the relative interior and the relative boundary. Yeah, it's the dimension is of the affine set. That's true, but it's a little more than just being a ball of that particular dimension. It's a ball that resides inside the affine.
Every point in Q is a boundary point. Every point in Q is a boundary point.
Every point in Q is a boundary point. Okay, so let's stop here.